Welcome back. Fitting equations to data is a great way to test our understanding of the behavior of that data. When we have a good model that we can express as an equation that fits well, showing the fit of that model is also a powerful way for us to demonstrate our understanding of the data to another person. So it's often the case that we would like to take a quantitative model and fit it to data. This is something we can do in Excel, but the defaults are rather limited. So what do we do if we want to have an arbitrary set of equations to fit to our data? We can do it, it just takes a few extra steps. So let's have a look at how to do that today. We can jump right into the data shown here, where we're looking at the median house price since 1963 in the US. I could plot this so we can see what we're looking at, and that might help us understand the model that we think we're going to have. Looking at this plot, what I can see is that the housing price since 1963 has increased, and it doesn't look like it's truly linear. I could test that using the built-in options inside of Excel by right-clicking and then saying Add Trend Line. It defaults to linear, and then it shows us as the dashed line that fit. And we can see that the data starts above this line, goes below, and then comes back above. And that's a classic indication that we have something besides just a linear trend. To me, this looks like it could very well be exponential. And Excel does have an exponential function built in. If I click on it, this does fit a little bit better, especially at low values, but at high values we get some strong deviation. And the reason for this is that Excel, as a default, does not allow us to handle this offset here. If I go ahead and say, display the equation for this fit, if we look at the equation, we can see that it is an exponential that is scaled by some factor out in front, but then there's no additional offset. So rather than an equation that looks something like y equals a times an exponential growth, we'd like to add in another constant c. Essentially what we're saying is that if we could, it would be nice if we had an equation that looked like this. A times exp, that's our exponential, raised to some factor, let's say tau is our exponential growth factor, times x, which would be our year. So if we want to, we could even say year here, that's fine. And then after this, we'd like to add in some constant c. And that's what's missing from this equation here. How do we do this? Well, Excel has a built-in solver. And so I think what we should do is we should just go ahead and illustrate that here. So let's say parameter and value. So we're not actually going to use the equation here, but we're going to leave it up so that it functions as a reference for what we're trying to do. The parameters in this equation are a, tau, and c. We're going to actually want, I think, one more, but let's not add it quite yet. Let's first think about how this equation is going to work. Essentially, it provides us a prediction based off of the x value. And so here we'll say predicted. And then what we want to do is just simply use this equation. And so we know that in Excel I can start an equation by saying equals. Then I could say a times, except I don't want to do this. I'd rather be able to use whatever value we finally decide for a. So I'll just click this box here. Then we'd like to have an exponential, and so when I type times exp, it brings up a function. Inside of this parentheses, then we type what we want to have, which is tau. But again, I don't want to type tau. I'd like to use the value of tau I will eventually put here, times the year, which is over here, and then plus the value we'll eventually put in for c. Now, one thing that I do think that would be nice to include is the fact that we're really starting with housing prices at 1963, but this is a lot like thinking about x equals 0. This is our starting point. And so, though it's not strictly necessary, I think it can be nice to include an offset. So let's say minus 1963. Then I have to have another parentheses here. And you'll see that Excel, when I have multiple parentheses, color codes them so they're a little easier to understand what goes with what. Now, instead of using 1963 like this, and I'll just hit enter, and the value is 0 because I haven't put anything here. What if what I said was a start year? And then I could say this is 1963. Now, I don't really know what I want to start with for A, so let's just start with 1 for A and for tau. For C, I have an idea. This is the offset, which is actually where this data starts down here. And that's also this value right here. So I'll simply just say that C should be equal to this value here. Now you'll see that I have a value of 1 greater than this predicted here. And the reason is that I have an offset equal to this plus this entire thing here, which, because I have A2, 1963, minus 1963, the exponential is 1. So I essentially have 1 plus the value here for my offset. It's not perfect, but it's very close, and that's good enough for us because we're going to let the solver inside Excel correct what we've put in for the different values over here. So I don't need 1963. In fact, I can also say that this should be referenced over here instead. What I would like to do then is take this formula and just bring it all the way down. But if I do that, I'll start having errors because as I go down, then the references that I have supplied for over here change, right? If I have this down here, those references are trying to read from values farther down, and they don't exist. And so let's go in, and all the parameters need to be absolute references. That means that they're in column H, and then cell 4 should not change. Column H, cell 5 shouldn't change. I shouldn't use an absolute reference for A2 because that's the X, and I do want us to reference a new X every time I go down. So I won't put one there, but I'll put one in front of H7 and H6. Now, if I go ahead and just double click here, it'll propagate down, and you'll see that we get reasonable values. And so let's just keep doing that. Insert another plot. Of course, the disadvantage of doing this is that we have lost the information for our fit line. We'll come back and check that in just a moment. But here we go. This is the data that we're looking at. Now I have values that are associated with my predicted ones. The blue line is the data. The orange is our predicted values. And you can see that it grows much too fast. So that's indicating that either the tau or the A are too large. So what would happen if this was 0.1 instead of 1? What if this was, and you'll see now that it has propagated through, that it's a little too low. So what about instead of 0.1, it was 0.5? Now it's too high again. And so you can see that we're doing a lot of guesswork here. I'm going to guess that maybe half of this is actually going to be a little bit better. And now I have a guess where at least I can see both lines. Maybe 0.25 is still a little bit much, so 0.23. And we'll see. We're not trying to make it perfect here. And you can see that if we had to adjust all these parameters to get a good fit, it might take a long time, which is why we're going to have Excel do this for us eventually. Let's just remind ourselves where we started in terms of the trend line and why we're trying to fit this. And so here's my exponential function that I would have had. And again, I can show this equation on the chart and make it a little bit bigger. However, the orange line, we're going to need to change. So what am I going to do? Essentially, we're going to run this through a least squared fitting routine. And what we want to do is calculate the residuals between our data and our predicted value, and then we want to square those residuals. And so I would call this residuals squared. I can essentially just type in that I would like to look at the difference between my measured parameter and my predicted parameter, and then I'd like to raise that to the second power. So that's going to be the residual squared. And then I can propagate that all the way down. In fitting, what we're trying to do is minimize the sum of these residuals squared. And so if I were to add up all of these numbers, I could then have a routine that attempts to minimize that final sum. We call this the sum of residual squared. So I'm going to say sum of squares residual, and this is equal to the sum of column B. Now I have a number that if I were to feed it into a program, it would know it's trying to minimize this. So let's go ahead and do that. Where we can find the solver is under data, and then you should have a button that says solver. If you don't, there is this tab here called analysis tools, and you can just click solver add-in and say okay, and then it will eventually appear here. That is how it works on a Mac. On a PC, the process is a little different, so you may have to Google how to add solver to Excel. Once we have solver, we can click on the button and it will bring up a dialog window for us. It's saying set objective. That's telling me what is the target cell I'm interested in. So I'm going to go ahead and select this. This is what we're trying to minimize. And you can see that we can either have it be maximized, minimized, or attempting to find a very particular value. But for us, we simply want to minimize this. And we're going to minimize it by changing our parameters. So these 4 parameters are what we're fitting or giving to our program. But the last one is simply an offset of years. So we only really need to change these 3. We're very confident in that these starts at 1963. So let's just fit these 3 here. Once we're ready to go, I'll press solve, and it's a somewhat slow process, but what it does is it changes guesses for these values, and then you'll see updates in this fit here as it attempts to minimize the sum of squares. Now what we'll find is that I do get a fit that looks a little bit better than what we expected over here. You may have got a slightly different result, and we'll talk about that in just a moment. When the solver's done, you'll get a dialog that says keep solver solution or restore original values, meaning changing what these are here. And we'll just keep the solver solution. So I'll say okay. Now, before we go into looking back at the solver for one moment, let's think about what happened. We told the solver change these values. These values are referred to in the formulas that give us a predicted value based off of the year. Every time we changed these, it updated everything in these formulas and recalculated the residual sum of squares that were based off of the difference between a predicted and initial measured price. That then changed the value of my sum of squares and did that until it reached the minimum value that it could. Let's go back and look at solver. There was a few other options that we needed to select. One of these was that we could choose different solver methods, and I think this GRG is going to be fine. But another one that is sometimes checked by default and you might want to look at is it says make unconstrained variables non-negative. Our unconstrained variables are the variables that we're attempting to fit or to change. It's the ones that we passed here, and you can see that our C value was negative. And so I'm going to go ahead and close this, and what if we had set this to 0? Our fit isn't very good, and that's fine. We'll go back to the solver. We'll use the same parameters that we had before where we're trying to fit these 3, but we'll say that it can no longer go negative. And so let's go ahead and solve. And what we'll see is before we had the best fit possible when this C was negative, and now it's not. And our fit looks still, to my eye, slightly better than the fit that we got out here from our basic exponential function. But in reality, it doesn't matter to me whether this is a negative number or not, the C, so I'll go back and say this was somewhere around like maybe 10,000. I'm not sure. I can't quite remember. Yeah, that looks a little bit better. And so we can go back to our solver, and then we can say solve while allowing this to be negative, and that's totally fine. And now we'll try to find the best fit. And we'll get something similar to what we had before. Now what we didn't get is an R squared. right? For instance, if I go back to this fit line here, there was just simply a button that said, tell me what the r squared is. And here it is, 0.9517. Pretty good. What's the r squared for this? Well, we're going to have to calculate it ourselves. But basically, if I think about what r squared is, it's pretty simple. I'll write the equation over here. It's going to be 1 minus the sum of squares residual minus the sum of squares total. So the sum of squares residual we already have. Here's my residual squared. This is going to be our total squared. I'll double click here so you can still see that we have the residual squared. What I'm saying is that I want to calculate the difference between this value that we measured and the average value of all the things that we measured. And then I want to take the square of that. And that's my total square. Then I just propagate this all the way down. And now my r squared is fairly simple. It's 1 equals 1 minus, and then I want the sum of my residual squared, we've already used this once, divided by the sum of the total squared, which is column E. And then when I hit return, I'll have an r squared value here, 0.988, which is better than 0.95 and agrees with sort of the intuition we would have just by looking at these lines. Okay, so now we know how to fit an arbitrary equation to data in Excel, and that opens up the ability to test very complex models. And so I hope you have fun going out and testing your understanding of your data by fitting equations that model your predicted behavior to that data.